Okay, so this is a homework assignment. This isn't one that I'm doing just to study. This is one that's actually for a grade. And it says two positive charges, QA and B, are placed on the opposite sides of a grounded sphere of radius r at a distance 3r and 6r respectively from the sphere center. Show that QB is repelled if the sphere from the sphere if QB is less than QA. So I really struggled with this question, so I'm going to try to be as detailed as possible and even take a step back a little bit and explain some of the, I guess, fundamental ideas to my knowledge of what exactly is going on. So the first thing I'm going to do is just draw a sphere. And this is just going to be me talking about the problem. I'll actually go after the problem here in a moment. Let me draw a better sphere. But what helped me solve this was when I took a step back and just kind of studied the idea here. So let's just say we have a sphere of radius r that's grounded. Now when it's grounded, it's just meaning that the potential is 0 around the circumference. That's all that means. Okay, so we have this point here. I'm going to call this point A. I'm going to call this point B. And I'm going to put a charge, probably will not be the color green. We'll do red. That's fine. And I'm just going to put a charge Q right here. Okay. And we still have our point A and point B. And I'm just going to give this some generic values. Let's say that the distance from the center to Q is just A. Okay? So that's how far the charge is from the center. Now, one of the interesting things with methods of images, which is what we're using here, and we're doing that because we have a conductor, in other words, we have potential of 0 around the circumference here, is you can disregard the circumference if you place an imaginary charge in such a way that it mimics the conductor itself. So what we can do here is basically pretend that this sphere isn't here. That this circle that I just drew, it's imaginary, it's not real. And we can do that so long as we place an imaginary charge in our circle called Q prime, such that it's mimicking the sphere itself. So the electric field, the potential, it's going to be, we're going to get the same result as if the sphere wasn't there at all. So kind of a interesting way to approach this problem. And we'll say that it's a distance, I don't know, B from the center. Okay? So the distance then from here, our imaginary charge, to our real charge, well, that's going to be just A minus B. So that's this guy. A minus B is just that distance. Okay? So let's see what we have. We know that the potential for a point charge, which is what we have, is 1 over 4 pi epsilon naught. And then using the principle of superposition, we can say our real charge Q over, I'm going to just call it R, plus Q prime over R prime. You could call it script R as well, whatever it is you'd like to call it. So this is our potential as a function of R. And what we're going to do is apply boundary conditions and relate Q and Q prime as well as the distances A and B. So we're going to apply, we're going to apply boundary conditions. So the first condition is if we look at this point, look at point A here, the potential should be 0 because it's along the surface of what was once our sphere, and the potential around there is 0 because it's grounded. So at point A, our potential as a function of r should be equal to 0. So let's plug that in. We still have our 1 over 4 pi epsilon naught q over r. Well, what is r? Okay, so our r in this case is going to be our big R. So that's just going to be the radius times, or not times, plus a. So that is the distance we're covering. So to get to this point A, how far is point A? Well, if you go a distance r, that puts you, I'll do that, I didn't mean to do that. If you go r from point A, you're at the center, and then if you go an additional a, little a, you'll be at point charge q. So hopefully that makes sense. The distance from point A to there is just big R plus a. So that'll be over big R plus a, plus our imaginary charge q prime over, so again, it'll go r, but a distance r will just take point A to the center, and we're also going to need to add this b to get to the position of our imaginary charge. So this will be r plus b, and this should equal 0 by our boundary conditions. So hopefully that makes sense. R is this distance, or I'm sorry, R is the distance from, point A to our charge Q, our real charge. And then R prime is going to be the distance from still from point A to this time our imaginary charge Q prime. So that's what these guys are. And hopefully you can see what those values are, and I just substituted them into here. And I'm applying the boundary conditions that the potential has to be 0 there. Okay? Well, what does that mean? That means that obviously I can multiply by 4 pi epsilon naught, and I could say Q over R plus A is equal to negative Q prime over R plus B. So I just subtracted that over. I subtracted the imaginary charge over R plus B over. Okay, so the other thing I'm going to do is I'm going to say big Q, or real Q, over negative the imaginary Q is equal to R plus A over R plus B. Okay. Cool, so we have that. Now there's a second point to consider as well, and that's at point B, B of R is equal to 0. And technically, you could pick out any point along this sphere, the potential should be 0. If I wanted to pick the point here, that potential is also 0. If I called that C, the potential there is 0. But C doesn't really make sense because of the, I mean, it would be difficult to get the, you could do it, but A and B are just easier to find. So that's why A and B were easier to do, because It's just a straight line. But anyways, that's where the points are coming from. That's why we picked those points. So at point P, the potential has to be 0. So we can set up the exact same thing. 1 over 4 pi epsilon naught Q over. Now at point B, if we want to find how far the real charge is from point B, well, it's not a distance A, right? Because distance A gets you into the center. Okay, so that's not exactly what we want. Instead, we want to do A, and then we want to take away R. A minus R gives us B. So we'll do A minus R. Hopefully that makes sense. We're basically finding, I'll do it in a different color here, this distance. This is our new, well, the R for this one, which hopefully you see is just A minus R. And then plus our imaginary charge Q prime over, so for Q prime, this time we're going to do R and we're going to subtract B. Okay? So if you take the radius and you subtract this portion, or if you take the radius and you subtract that portion, you'll be left with just the distance that it is from the point B. So this will be R minus B. I think everyone's okay with that. That's just the idea behind it. And to fulfill the boundary conditions, this must also equal 0. And I can do basically the same thing as before. Now I can say Q over A minus R is equal to negative Q over R plus B. And from that, I can set up the exact same thing I had before. If I divide over by negative Q and multiply over by A minus R, I get A minus R over R minus B. Okay? So I'm going to call this equation 1. Oh, that might be confusing. This is equation 1. And this is, we'll call this equation 2. But notice how the right-hand side for both of them is equal to our real charge divided by the negative of our imaginary charge. Well, that tells us that R plus A over R plus B should equal A minus R over R minus B, right? Now we can cross multiply and distribute. You'll get R plus A times R minus B is equal to A minus R times R plus B. And now we can distribute. And what do we get? Well, we'll get A squared minus BR. So R squared minus BR plus RA minus AB. And that's going to be equal to AR plus AB, minus R squared minus RB. Okay? So what happens here? We have this and this will cancel. We add them over. Yeah, that one does cancel with this one, right? Okay, so that cancels, and we can just add AB and R squared. And we get 2 R squared is equal to 2AB. And if we solve for B, obviously the 2's will drop. B is equal to R squared over A. Okay, so I'm going to box that because that is one of the equations that our professor gave us in class to use, but for me it is really helpful to work this out and to see like, oh, okay, this is why that works the way it does. That's why it's equal to what it is. For some people, this might have been a huge waste of time, the first part of this video. Sorry about that. But if you are like me and you understand things better when you work through something like this was very helpful for me. So that's why I went ahead and did this. If you're obviously in the same class as me, then you could have skipped all this. You don't need to show this. I just did it for my own benefit, and hopefully it maybe helps other people as well. So almost done though. So now that we have B, we can plug, I'll call this equation 3. And if we look back on equation 2, we could plug B into here. Right? We could plug B into here. And so we could plug into there, or we could plug it into just right above here. So you could plug it in there, I suppose, but just to save me some steps, I think I'm going to plug into here. And this should be Q prime. This should be Q prime. Did I forget Q prime anywhere else? I think I did it up here. Sorry about that. Okay. So I think I'm going to go ahead and plug it into there. I think that makes the most sense. This should be a minus B though, shouldn't it? Yeah. And I did that here, so cool, good. Just double checking my work, making sure I didn't make any other mistakes. I think we're good. Okay, so I'm gonna plug that into there, and we get Q over A minus R equals negative Q over R minus R squared over A. Now, why am I doing this? Well, now I can get a relationship between Q and Q prime. We are also given the equation for Q prime. You didn't really need to know that for this problem if you wanted to just use it, but again, it helps me. So we can cross multiply, of course, and what do we get? We're going to get QR, Q times R, minus QR squared over A equals minus Q prime A minus R. Okay. So that's what we have there. I think we're all good, just double checking everything, that I didn't make any mistakes over here. Everything looks good. Checking my notes. Good. Okay, so now that we have this, we can then say this is negative QR, R minus A over A. Another way to think about this is if you just got common denominators and factored out a Q, you would have RA. Actually, if you factored it out, let me do it here. I could factor out a QR, and I'll be left with 1 minus R over A, which is just going to be A. So this would be QR, A minus R over A, which is exactly what we have. The only difference is I factored out a negative. This is still all equal to Q prime A minus R. So then if you factor out the negative, you get minus QR times R minus A over A is equal to, so this had a negative attached to it. I just moved it over, so we had a Q prime. Okay, so that's good. You could also actually distribute the negative. So if you there was a negative here, So if we distribute it, then you'll get Q prime R minus A. This was still equal to negative. I probably should have wrote this out. Okay, so I just distributed this negative. Okay, cool. So now we're there, and now we're just going to solve for Q prime, and we can do that by dividing over by R minus A, R minus A. Those obviously will go away, and we'll get Q prime is equal to negative R over A, because that doesn't change, times our real charge Q. And this was the other equation he gave us, and this is why it works. Okay? So again, you didn't really need to do all this, but I think you need the equations to do the problem, and it helped me to see where it came from. Okay, so with all the background information, I think I feel a little bit more comfortable attacking the problem. So let's actually begin the problem. So we have a sphere, just like before, of radius R. And I am going to draw some lines here. Oops. I'll draw the straightest lines, so that's a good tool to use. And we'll call this line, this point here, QA, which we know to be a distance 3R. And then in red, it's not necessarily to scale, but this is where QB is, which we know to be a distance 6R away. Okay, so the first thing is we need to put our charges inside our, well, it's no longer really a sphere, we're pretending there is none, such that you get the same results. So I don't know exactly where they're going to be, but I know they're going to be inside. I'll call this Q prime of A, and the distance from the center will just be A, and also Q prime B, which I'll call a distance B from the center. So those are our two imaginary charges. The sphere itself basically doesn't exist. We're getting rid of the conducting sphere and replacing it with two imaginary charges, Q prime of A and Q prime of B. Okay, so now with that, I'm going to write out some things that we now know comfortably, which is that Q prime of A is equal to negative R times QA over A, and Q prime B is minus R QB over B. Okay? So we know a few things there. That's pretty handy to know. And we're looking at the forces because we want to know, we want to show that QB is repelled from the sphere if QB is less than QA. So when we're dealing with these forces, we're going to use Coulomb's law, which Coulomb's law says, if you forgot, Q1, Q2 over 4 pi epsilon naught script R squared, R hat. Okay. So we're going to basically be looking at all the forces that would be acting on charge B. So we have QA, the real charge, but now we also need to consider the force that would be exerted on from our imaginary charges as well. And we need to add those three charges up to find the total charge, or the total force. We need to add all the forces up from those three charges to find the total force. So if we do the summation of our forces on QB, that would be just the force QA exerts on QB plus the force QA imaginary exerts on QB plus the force QB imaginary exerts on QB. Okay. So now we can set it up. Well, each term is going to have a QB because we're going to multiply by the charge that's feeling the force. And each term is going to have a 4 pi epsilon naught. Those are constants. So I'm just going to factor those guys out. And we have QA over the distance from A to B. Well, the distance from A to B, we know the distance from B to the center is 6A, and the distance from the center to QA is 3R. I'm sorry, did I say 6A? I meant 6R. The distance from QB to the center is 6R, and the distance from the center to QA is 3R. So the distance from QA to QB is 9R. So this would be 9R squared. I'm going to make this parenthesis bigger because it gets messier. Plus Q prime of A, so the imaginary charge. So how far is our imaginary charge A from QB? Well, we know 6R takes us to the center, so it's a distance of 6R plus the distance Q prime A is from the center, which is A. So the distance is 6R plus A squared plus our imaginary charge from B. So B is not quite 6R, it's actually a little bit closer, right? So if we do 6R minus B, that'll give us the distance from our imaginary B charge to QB, right? So that's 6R minus B squared, and this will all be in the I-hat direction if we're letting our coordinate system be like y, x, so it's in the x-hat direction. So now we're going to have to do a few substitutions. So what is our A here? Well, we can basically use what we found earlier, where A or B is R squared over our A, right? So for R's, if we're looking at A, right, you're going to have R squared, still in the numerator, divided by our 3R, and that is just the distance there. So we have R squared over 3R, which is just R over 3. Okay, so hopefully that makes sense. And that's coming from what we found earlier. B is R squared over A. Okay, and A is the distance from our charge to our center. All right. Well, we can use that same reasoning to find B. B is going to be R squared over 6R because for charge B, it's 6R away, which obviously just simplifies to R over 6. Q prime of A, well, now we can use the charge the charge equation we had there earlier, which are these. The only difference is now we know A and we know B. So I'm just going to substitute the A and B that we found right above into it. So you get minus RQA over R over 3. And for Q prime of B, you get minus RQB over R over 6. And then simplifying our imaginary charges here, you get minus QA over 3. And the imaginary charge B is minus QB over 6. So I'm going to box this whole thing. Okay, so that's all of that. So hopefully that makes sense. We're just basically applying what we knew into this. And now we can plug in. We can plug in our expression for A and B, R over 3 and R over 6. And we know what Q prime A is and Q prime B is in terms of Q A and QB. So I'm just going to plug it all in. So we have QB over 4 pi epsilon naught. The first one is easy because we know that's just going to be QA. 9 squared is 81 r squared. Let me make this a little bit bigger. Minus QA over 3. So that's my Q prime over 6r plus r over 3. That's my A squared. Minus QB over 6 all over 6r minus r over 6. That was my B squared. Okay. So now what I'm going to do is I'm going to get common denominators there. So we get QB over 4 pi epsilon naught is QA over 81 r squared minus QA over 3 all over, so let's see, that's going to be 6, 12, 18r plus r, so 19r over 3 squared minus QB over 6 over, let's see, that's 36r minus r, that's 35r. 35r over 6 squared. And we can obviously square all that. So QB over 4 pi epsilon naught. We have a QA over 81 r squared minus QA over 3 times, so I'm going to flip my bottom fraction and square everything. So we're going to get 3 squared is 9. 19 squared is 361 r squared minus QB over 6 times 36 over 1225 r squared. So I just flipped and squared. So let's see. QB over 4 pi epsilon naught is what? Times what? QA over 81 r squared minus, that's going to be just a 3. So 3 over 361 r squared QA minus, let's see, that's going to be boom, boom, 3. Let's see, flip it. Did I do that right? Oh, that's 36, not 6. Duh. Whoops. That actually would just be boom, boom, 6. Minus 6 over 1225 r squared QB. So here you could get common denominators, obviously both right here. So let's see, QB over 4 pi epsilon naught. So that's going to be 118 over 29241. While we're at it, I'm going to go ahead and factor out an r squared. So 4 pi epsilon naught r squared QA minus 6 over 1225 QB. Now that's basically everything. So this is the summation, and this is in the x-hat direction of our forces. I dropped the notation pretty early on, but it's okay. So what does this say? Well, if QA is bigger than Q, because this number is bigger than this number, So long as QA is greater than QB, then we're going to get a positive number, which means QB will be accelerated in the plus I hat direction, which means it'll be repelled away from the sphere, because the plus x hat direction is obviously, this is the plus I hat direction, so it's going to be repelled away. Okay, so that's basically the problem. A few pitfalls to keep in mind. Oops, putting my pen up, sorry. A few pitfalls to keep in mind is, well, for me, it was really where we put the charges. So I originally thought maybe we could put the charges outside of the sphere to get the potential to be 0, but that's not going to work. We would still have a potential elsewhere. So to keep the potential 0 inside the sphere, I have to mirror it inside the sphere to undo what's being done. So that's one thing to keep in mind. The other thing to keep in mind when you're doing this is to use superposition. So this, at least for me, it's nice to break this down into basically 3 separate parts and add them together. So you can break this up and think of it as 3 separate individual questions, smaller individual questions. So you can use superposition. So those are things to keep in mind. The other thing that might help you is the earlier part of this video, where I kind of showed why this works. That really helped me, and it helped me understand why it is what it is. So that's that. Be very careful with your algebraic mistakes. I made a few. Let's see, what else to keep in mind? Our substitutions. Keep in mind the substitutions and why they work. Again, that's why the earlier video helped me out, instead of just kind of blindly applying equations. Keep in mind why we got what we got here. And for the most part, it's algebra, a lot of simplification, so be careful of your algebra. And just the idea knowing that if you're accelerating in the plus I hat direction, then your charge is being repelled. So hopefully that helps somebody. It helps me, so I guess it already did what I wanted it to, but hopefully it helps someone else as well. So that's everything.